on to part 2 of our revisitation of space-time diagrams. And the subject here is quote-unquote cool plots, quote-unquote don't be a square. I don't know how it translates into other languages or something, but the idea is if you want to be cool, you want to be with it, then you don't want to be a square. What does that have to do with what we're doing here? Well, as you'll see, maybe just you can see from the diagrams already, we're doing some sort of strange type of plotting here. So let's see what we've got. Non-square plotting, to bring it back to don't be a square. If you don't like that reference, you can ignore it. It's not important for our purposes here. So here's our normal, we're just doing XY plots to start off with here. Okay, so we've got 2 dimensions, x-axis, y-axis. You could imagine maybe we have a field or a whiteboard, and we want to plot points in the field. Or a surveyor, maybe we want to mark locations of various things within a field, or just mark locations of various things on a flat surface. And clearly we have our scale on here. So this is x1, y1, this set of axes. This point here is x1 equals 2, so 2 over for x1, y1 equals 3. The point 2, 3 there. Nothing surprising about that. But you could say, why do we have to have our axes at right angles? This way we've always done it, and maybe it makes sense in some ways, but if you think about it, there's clearly no reason why we couldn't do it this way. We couldn't have the x-axis horizontal again, and the y-axis at some angle. So let's just consider that a minute. Note that the plot then, if I'm going to plot the point x2, so I've got x2 and y2 versus x1 and y1 over here, so a separate set of axes now. x2 equals 2, y2 equals 3. So note how we plot that. So we go again over x2, but then we go up parallel to the y-axis, the y2 axis. So that's 1, 2, 3 there. So that's our point x2 equals 2, y2 equals 3. And we're going to come back and do a comparison of these two situations in just a second. But we could go one step further and say, hey, let's get really wild here. Why not put the x-axis at an angle as well? And so that's what we've done in our third example here, where we've tilted up the x-axis at some angle. We've got the y-axis tilted at some angle as well. And so in this case, with the x3 and y3 axes, the point x3 equals 2, y3 equals 3. Again, we go 2 on the x3 axis, and then parallel to the y-axis up 1, 2, 3. And so that's where the point is on that plot. Now, I hope if you think about it a minute, you can see that if we're plotting a field, surveying a field, or just points on a flat surface like the whiteboard here, any one of these would work as long as we're consistent about it. Again, it'd be a little strange to do it in these second two cases, but we could certainly do it. We could say, let's define the x and y axis like this, and then for any given point on the board here, we could say, okay, that has an x3 value, so maybe over here, you would have a negative x3 value over here, and a sort of a negative y value too, y3 value, and so on and so forth. So any given point could be plotted with the x3, y3 coordinates, or the x2, y2 coordinates, or the x1, the normal, quote-unquote normal x1 and y1 coordinates. Note that I could use any of the three of them, but note that the 2, 3 point in each case is actually a different point on the board. Let's assume that if we superimpose all three of these so they all have the same origin point, so we took this origin here, put that on top here, and took this one and put this on top here. I won't draw it because it gets really messy. It's hard to draw it. But if we superimpose all three of them, especially in this case, you can see clearly the x3 equals 2, y3 equals 3 point would be way up there. So if we moved that over here and superimposed it here, then that point would probably be, just roughly speaking, be someplace up here. Okay? Would be different from the x1 equals 2, y1 equals 3 point. And in fact, for this one too, again, we didn't draw it quite to scale, but it clearly would be at least over this direction more, someplace, might be up here someplace or something like that. So the point being is the coordinates of our three systems are different. Okay? So if I do 2, 3 here is a different point for 2, 3 here is a different point for 2, 3 there. Again, assuming I have all three of them superimposed with the origin at the same point. Another way to think about that is If I have, let's do the most obvious example. If I have this point here, okay, and I'm measuring it in those coordinates, and I get, okay, x3 equals 2, y3 equals 3 for that, what would those coordinates be if I transform them into the x1, y1 coordinates? Because it's a different point, okay? This 2, 3 point here in this coordinate system is a different point than the 2, 3 point in this coordinate system. In fact, as we've drawn it here, just roughly speaking again, by eyeballing it, let's say it's up here. So this is the y3, oops, not y3, x3. x3 equals 2, y3 equals 3 point. If we superimpose the two, that point we're talking about is right there. And we can ask the question, what's the value of that? So let's just get rid of this for the moment here. What is the value of this point in the x1, y1 coordinate system? Well, again, just sort of eyeballing it, we can see, okay, it's something like this, like that, and maybe 1, 2, 3, 4. So maybe it has a value of x1 equals 4, and y1, 1, 2, 3, 4, maybe 5, 4, 5, or something like that. Okay? I hope that reminds you of something. It should remind you of things like the Galilean transformation and the Lorentz transformation, because in those cases, we're transforming between coordinate systems. We did a lot of examples with the Lorentz transformation with Alice and Bob. Alice having her frame of reference, Bob having his frame of reference, and Bob has a certain coordinate system in his frame of reference, and using the Lorentz transformation, if he has any given point, space-time point in his frame of reference, we transform it into Alice's frame of reference, her coordinate system in space and time, using the Lorentz transformation. Same exact idea here. We could have this coordinate system here. For whatever reason, maybe Bob chose this crazy-looking coordinate system. Alice chose a more regular, normal system. And they would want to, if they were both surveying the same field, using the two different coordinate systems, they would have to have a transformation between them. So if Bob measured something and say, hey, I got that, that well over there that we're surveying for in our field is at point 2, 3, x equals 2, y equals 3, would not be Alice's coordinates for the well, x equals 2, y equals 3. It'd be something else. Maybe, as we said, maybe 4, 5 there. Okay, so that's why we're introducing this idea, because as we will see in the next video clip or so, is that this type of thing is going to be useful, because what we'd like to do is put both Bob and Alice on one plot using two coordinate systems. So two coordinate systems in one plot. So the idea is something like this. We're going to superimpose it on our regular type plot so we can get an idea of what's going on in this Lorentz transformation back and forth between the two frames of reference. Before we finish this video clip, though, I want to make one other point here, and that is we talked about lines of simultaneity in a previous video clip. Really, lines, we'll say lines of same location first, and lines of simultaneity, or lines of same time. Same time, so that's simultaneity. Okay, remember, lines of same location are lines in our coordinate system that mean everything happens at the same point in time. And remember also on our regular coordinate system, lines of same location are just vertical lines at any given point. Extend it down below too for negative time if we want. So that's the x equals 2 line of the same location. Anything that happens at that location at any given time will be on that vertical line. And then lines of simultaneity, lines of same time, are the horizontal lines on this plot. So they say any event that happens at the same time that is simultaneous with another event, both those events will be on the same horizontal line, the same value. Now, let's see, I was using generic values for y here, so now we're talking about, let's change this now to our t values, because we can certainly do a plot with, instead of xy, surveying like a plot of land. Now we're going to survey space-time. And space-time in one dimension. So we have the x-axis for our dimension, and then time axis for the other dimension. And so this becomes T3 here. Okay, so now we've turned them into space-time diagrams. Same idea applies. Any of these are valid, just different ways of doing it. But just because we measure at 2, 3 in one position here, and actually then let's change all these two. Be consistent here. So this is T2, T3, and we've got a T3 here, and so on and so forth. Just because we measure an xt point, a space-time point there with certain coordinates, it's going to have different coordinates in another coordinate system. And really, if you think about it, that's what's going on with the Lorentz transformation. Bob measures an xt event, an event at a certain xb and tb location. We transform it into different coordinates in Alice's frame of reference using the Lorentz transformation. So back to the point here, though, lines of same location, lines of same time, or lines of simultaneity. Vertical and horizontal here, note that they're parallel to the respective axes. And same thing when we get these skewed plots, as it were, these non-square plots. The lines of same location here are going to be like this. They're going to be parallel to the t-axis because the t-axis is the line of same location for x equals 0. Oops, that's not a t1 there. Sorry about that. It should be a t2. But anyway, same lines of same, curved line there. So lines of same location on this plot are parallel to the time axis. Lines of same time, because the x-axis is horizontal here, are still going to be the horizontal lines there. So that is what our lines of same location, same time, lines of simultaneity would look like. Again, the horizontal lines being lines of simultaneity. On our third plot here, though, both lines are skewed. And again, they're always, the lines of same location, same time, are always parallel to the appropriate axis. So that in this case, I've got lines like this, roughly not crooked, of course, but nice straight lines as much as possible, like that. Those are the lines of what? Well, those are the lines of constant x values, so constant location, same location. Those are the lines parallel to the t-axis. Lines of simultaneity are the lines parallel to the or the x-axis. So they go like this. Okay? So it's important to sort of get that concept down because we're going to be using that in the next video clip or 2 or 3. It'll come up very shortly here. Okay, so again, cool plots, don't be a square. So non-square plots, perfectly legitimate. We usually don't use those, but we will find that a plot actually like this, we're going to superimpose it on a plot like this because we'll find that that's what the Lorentz transformation is telling us to do when we're going between one frame of reference to another frame of reference. So that's coming up. Space-time diagrams part 3, and now we get to bring in the special theory of relativity. So we've got one of our standard situations here. Let's revisit it. We'll have Bob traveling in a spaceship and in the positive x direction to the right at velocity v. Alice will be observing. And if we wanted to plot Bob's world line in Alice's frame of reference, it looks something like this, of course, depending on what the actual velocity was. But the slope here is simply going to be 1 over the velocity, as we've talked about and reminded ourselves in a previous video clip here. These dots here are not important. I was just sort of trying to get a nice plot there. So we can see actually if we wanted to calculate the velocity here, and we're assuming from now on that our units are going to be, say, in light years for x and years for time, or perhaps light seconds for x and seconds for time. But that gives us c, of course, speed of light being 1 light year per year or 1 light second per second. So again, if we were to plot a light beam going out from the origin, it'd be at a 45-degree angle, slope of 1 here. And we can see Bob, at least on our plot here, is traveling such that looks like in 2 years, say, he goes 1 light year, right? And in about 4 years, he goes 2 light years. So it looks like he's going at about 0.5, 1/2 the speed of light there. So this, the slope would be, actually the slope is 2 here, and therefore velocity is 1/2 In other words, 1/2 the speed of light. And so that would be Bob's world line in Alice's frame of reference, straight line, because he's going at constant velocity there. If we were looking at it from Bob's perspective, from his frame of reference, of course, he's sitting in his cockpit. As far as he's concerned, he's at rest, in his lattice of clocks and so on and so forth. And he sees Alice receding behind him. So it looks something like this to him if he was to plot Alice's world line in Bob's frame of reference. He would see Alice receding backwards. So the slope here, if we were to put that in, slope equals -1 over v. It's sloping downward. And so essentially Alice is going at -0.5 the speed of light to the left as far as Bob is concerned. And so we can see there's symmetrical situations there. That's how Bob sees Alice in his frame of reference. That's how Alice sees Bob in her frame of reference. Now for any given point, though, remember, we have the Lorentz transformations. So given, say, in Bob's situation, a given space-time point, like this one right here at -2, 4, if I wanted to find the corresponding point in Alice's frame of reference over here, it would not be -2, 4. Okay? So this point here, -2, 4, I'd plug it into the Lorentz transformation. That would go from Bob's frame of reference to Alice's frame of reference. So this is sort of our standard one here. We could plug in the coordinates for Bob, that point he measures in his space-time point in his frame of reference, and we could find the corresponding coordinates in Alice's frame of reference. So obviously we need v, so we could calculate gamma and do the calculations and get the actual results there. Or if we had a point in Alice's frame of reference, she sees a flash of light, an event, or something happens at a certain x and t value in her frame of reference, we could figure out the coordinates that Bob would see it in his frame of reference using our second set of transformations. And remember the minus sign here. So our standard situation, our standard set that perhaps we memorize, is this one where we have the frame of reference, in this case Bob moving to the right, Alice observing, and then if we have the opposite situation where something is moving to the left, we just change the minus sign and be careful that we have everything set up correctly there. So that's nice. What we'd like to do is somehow, could we put Bob's plot on the same plot as Alice's plot? And because it's just not a one-to-one correspondence, you can't just take this and put it over here. The Lorentz transformations tell us it's going to be a little bit more complicated than that in terms of going from a certain point in Bob's plot to a certain point in Alice's plot. In the previous video clip, we had those skewed plots, as it were, those non-square plots, to show you how it might work. And this is going to be very similar to that. We're going to do it semi-quantitatively. We're not going to go into all the details to do it precisely, but we want to get the basic idea here, because as we'll find, it's going to be useful later on, which is why we're doing it, of course. So let's start off and just say, okay, here's the T sub B axis in Bob's frame of reference, right? And actually, remember, that would be the line of same location. That is xb equals 0. So that's actually Bob's location in his frame of reference. The x, if we were to draw his world line on here, Bob's world line, it would just look like this. Go right along the x-axis there, the x sub b axis, because that's where he's located in his frame of reference. He never moves from that position. Same thing for Alice in her frame of reference. Her position would be, her world line would be, right along the x sub a. The T sub a axis at xa equals 0. Okay. So our question here is then, if we want to draw the T sub B axis in the context of Alice's plot here, what do we have to do? Well, essentially, we just have to plot Bob's location. The TB axis in his frame of reference is his location. Well, we've actually already done that. This is Bob's location at any given time in Alice's frame of reference. So actually, we can even just say something like this. We'll erase the Bob there. Put a little arrow on here. This is the TB axis. Bob's T sub B axis in Alice's frame of reference. That's his line of same location. in Alice's frame of reference, his line of same location is that. That's the line, the world line he's on. Here, it's just a straight vertical line. Okay, so we see it skewed a little bit. Maybe you can see now the similarity to what we were doing in the previous video clip. Could we actually, that's sort of qualitatively, could we do it quantitatively as well? And yes, if we look at the Lorentz transformation here, and we say we want TB equals 0. Okay, so we're going to say we want TB equals 0. I'm sorry, no, not TB equals 0. We want the TB axis is XB equals 0. That's Bob's location. Okay, so we're concentrating on the TB axis here. XB equals 0. Let's look at our equations here. And a particularly nice one is this one right here. Okay, let's just write that down over here. In fact, XB equals gamma XA minus VTA. I've got XB equals 0. The Lorentz transformation says that's equal to gamma times XA minus VTA. That's a true equation. And if XB equals 0, then we can see this thing equals 0. And that also means that, just to be clear about, let's just put an equal sign over here. This means gamma XA minus gamma VTA equals 0. Just multiply through by gamma there. And then bring this to the other side. So what that means is gamma XA equals gamma VTA. And those of you who've done a fair amount of algebra recently, you can jump ahead and see this in your head already. But what's our result then from this? Well, the gammas cancel. We have a gamma on each side, so we can get rid of those. And we're just left with XA equals V TA, or another way we can write that is TA equals 1 over V X sub A. Just divide each side by V and sort of switch the order there. Okay. The reason I wrote it in this form here is because this is our standard form for writing. You may recognize that as an equation of a line. Way back when we did a little math review on that. We're not going to push this too hard here. But quantitatively, for those who are familiar with this, essentially the T value here is my vertical axis. The X values are the horizontal axis. And the 1 over V here is the slope of any line that I've drawn here. So this is telling me that when XB equals 0 for Bob, which is his TB axis, the equivalent line on Alice's frame of reference is of this form. T sub A equals 1 over V X sub A. And that is exactly this line here with slope 1 over V. It goes through the origin. For those of you who remember about the y-intercept of the equation of a line, the y-intercept is 0 here. Again, we're not going to push that too hard. For those of you who are very fuzzy on it, I can't remember what we're talking about there. The point being here is that by setting XB equal to 0, that is the TB axis in Bob's frame of reference, and using the Lorentz transformation, we can find the coordinates of the TB axis, an equation really for those coordinates for the world line in Alice's frame of reference. It turns out to be a line like this with slope 1 over V for whatever the velocity of transformation is there between the two frames of reference. Okay, so we've drawn part of Bob's frame of reference now in Alice's frame of reference. You also might say, before we go on to the x-axis here, what about, this XB equals 0 is a line of same location. What about other lines of same location? Okay, so over here, lines of same location are good in green here. That's the same location. That's XB equals 1, 2, 3, and so on and so forth, or 1.5, whatever you want to do. Could we transform these lines of same location and also put them on this plot here? In other words, we're starting to take Bob's grid, the vertical lines here at least, and reproduce them on Alice's plot. Well, to do that, just to indicate that, this line is, that's 1 right there, XB equals 1, we'd say XB equals 1, and by the Lorentz transformation, that equals this equation, gamma XA minus V T sub A, and just a little bit of similar algebra here. We could get an equation out of this, somewhat similar to this, although this time we'd have a y-intercept value in there. And what we'd find is we get a line something like this. Let's get rid of the slope part here now. We've seen that. So we get, well, not quite like that. Let's get a little straighter than that. Try to get it in here. Something like that. In other words, it would be parallel to the TB axis. Just like the lines of same location here are parallel to the TB axis, when we transform it to Alice's plot, the lines of same location will be parallel to the TB axis. So they'd be diagonal lines like that, parallel to this TB line we have here. This is how you could do it actually quantitatively, mathematically there. Okay, so the vertical lines over here in Bob's frame of reference, his grid, the space-time grid, transform into lines at an angle, slope 1 over v actually, and then the lines of same location for each of these would transform into parallel lines over here. Okay, so that's part of the grid. That sort of takes the lines of same location in Bob's frame of reference and transforms them into lines of same location in Alice's frame of reference. Now note that Bob's lines of same location are at an angle here. Alice's lines of same location, of course, are still vertical lines here, so they're different. A line of same location for Bob is not a line of same location for Alice. Okay, now let's look at, okay, so we did this. Let's look at now the XB axis. We like to take the XB axis here, and what does it look like if we put it on Alice's plot? So, XB axis. So, we want the XB axis here. And the XB axis, of course, is when TB equals 0. Times T sub B equals 0 here. Okay, so T sub B equals 0. And if we look at our equations over here, we can use different ones, but this one in particular is a nice one to use because we've got the TB all by itself here. It's going to equal 0, so we can say this equals gamma times TA minus V over C squared XA. Okay, and again we'll just say that equals 0 because for this special case, for the TB equals 0, the X sub B axis, well, we can solve this equation for XA in terms of TA. In fact, we won't multiply it out this time because we should be able to see that if I've got something times something equals 0, that means either this is 0 or this something is 0. Clearly, gamma is not 0. It's greater than or equal to 1. That means this must be equal to 0. So this implies that TA minus V over C squared X sub A equals 0. And from that, we get T sub A equals V over C squared X sub A. And that is our result for it. And again, if you look at that, you say, in Alice's frame of reference, with T being the vertical axis, X sub A being horizontal, this is the equation of a line with slope V over C squared. Okay? And no y-intercept actually. So what that would look like if you actually put in some numbers here and plotted it, we'll just give you the result here, is it looks something like this. Let me see if I can get this more or less. Well, it's something like that. That would be the X sub B axis, because remember, so X sub B axis is when TB equals 0. So we plugged in T sub B equals 0 using one of our Lorentz transformation equations and got an equation that is true when T sub B equals 0. Okay, that's important. This equation is not true just in general. It's true for the case T sub B equals 0. So Bob's horizontal axis here, the XB axis, transforms into Alice's plot as a line with that slope, as you can, in fact, slope V over C squared. And we could do lines of simultaneity as well. Again, the lines of simultaneity here would be T sub B equals 0, T sub B equals 1, T sub B equals 2, or really any T sub B. T sub B equals 3.896, is a line of simultaneity. And again, to do that, same idea here. We just say T sub B equals 1, Okay, that's a line of simultaneity here. This line of simultaneity for Bob equals, again, our equation gamma TA minus V over C squared x sub A. And we could solve that again, put it in a form somewhat like that. And we'd find that the lines of simultaneity for the x and b axis here on Alice's frame of reference would be parallel to the x sub b axis. So they look something like this. And the lines of same location, look something like that. And now that should look familiar to you, especially. This was our case we did in the previous video clip, where we did over here on this side, where we had the very skewed axes, both of them at angles that were not vertical or horizontal. And that's why we did it, to show that now we have both Bob's frame of reference and Alice's frame of reference, or really their space-time diagrams, on the same plot here. And so note that any given point, let's do a red point here. Okay, let's just put, let's do a relatively easy one here. So we'll do it about right here. Okay. Now, imagine if we went back to the surveying example and we were doing a plot of land. That red dot would indicate a certain position at that plot of land. And that's constant. It's invariant. It's just that, say, the location of the well on the plot. On a space-time diagram, that red dot represents an event, say a flash of light. You could take a photograph at that position and verify, yes, that's where it is. But as we've seen, Bob and Alice would have different measuring systems for saying exactly what location and what time that occurred, and we can get that now off of these plots. So this event here, one reason I chose it, because it's very easy. In Alice's frame of reference, she said, I saw that flash of light, took a photograph of it, and it was at x equals 3, t equals 4. Okay, so at time t equals 4, maybe 4 years, and 3 light years away from my origin, that flash of light occurred. And then the question is, where does Bob measure that flash of light in his coordinate system? Well, it's a little trickier than we can do on this diagram. We'll talk about that a little bit more in the next video clip. But clearly it's not at 3, 4. 3 over and 4 up. For Bob, maybe it's at something like this is like 1, 2, and then 1, 2, maybe 3. So roughly 2, 3 in his diagram. Now that's very qualitative. It's not going to be exactly like that. But hopefully you see the idea here that by putting both coordinate systems really on the same plot, first of all, we have to skew Bob's axes here to get to work. But we can still see his lines of simultaneity. They're not going to be just vertical and horizontal. They're going to be parallel to the XB axis for the lines of simultaneity and parallel to the TB axis for the lines of same location. So to Bob, anything that happens along this line here is simultaneous to Bob, or that line. Anything that happens on one of these lines are things that happen at the same location throughout time. And so Bob himself in his cockpit is sitting on this line, or really moving along that world line as he moves through time here. Okay, so we're going to exploit this a little bit later on, especially when we look at things like the twin paradox and the pole in the barn paradox, and we'll also do some more examples of this as we go along.